Bar's main research interest is in the foundations of cryptography with the focus on secure multi-party computation. And today he'll tell us about perfectly secure two-party computation for symmetric functionalities with correlated randomness. Bar, over to you.
Okay, so thank you for the introduction. Thank you for coming and inviting me. Today I'm going to talk about perfect security in two-party computation with correlated randomness. And this is joint work with Olga Nissenbaum, Eran Omri, Anat Paskin-Cherniavsky, and Orpita Patra. Okay, so I'm going to start with just the definition, what we're talking about. So in our setting, we care about secure two-party computation. Here we have two parties, each of them holding an input. They interact in some way according to some specification of the protocol. And at the end of the execution, each of them obtain the output. And the parties wish to do this computation securely. So intuitively, we want to have privacy, so no party learns more than the output and its input revealed. We want correctness, and we want also fairness and guaranteed output delivery. And the way we define this is via the real versus ideal paradigm. And in this work, we care about perfect security, which roughly states the following. So we take the real-world protocol, and we compare it to an ideal version of this protocol. And in this ideal world, the parties have access to a trusted party that does the computation for them. So each of the parties sends its input to the trusted party computes the function, and sends the output back to the parties without them having to interact with each other. And we say that the real-world protocol is secure if it emulates the ideal world. In more details, we want to ensure that for any adversary corrupting one of the parties in the real world, there exists an adversary called the simulator in the ideal world, corrupting the same party that is able to simulate the attack, simulate the view and the output of the honest parties in the ideal world. And in perfect security, we wish these two worlds to be identically distributed. So this already seems like a very, very strong definition. So I mean, we don't have an honest majority. We have we want perfect security with guaranteed output delivery. It seems to be very strong. So what we do in this work is augment the real world, or because it seems to be such an impossible task, we augment the real world with correlated randomness. And in this model, the parties, before receiving their inputs, they go to another party, which is also trusted, but unlike the trusted party from the ideal world, this party is only able to sample correlated randomness from some input, from some distribution. And then each of the parties receive its part of the randomness. And only after receiving the randomness, the parties obtain their inputs, they interact with, in the protocol, and obtain the output. Okay, so this is the model that we care about. And the question is there something that can be computed? If so, what can be computed? What cannot be computed with perfect security in this correlated randomness hybrid model? So before talking about our results and what was already known, I first want to talk about why we should even care about perfect security. So I have three main points. So first, this is a natural theoretical question. And the second, this is a part of the general secure computation. So understanding it, this setting will help us understand the more general setting of secure computation. And finally, notice that because the protocol admits perfect security, there is no security parameter and there is no security parameter. We want the real world and ideal world to be identically distributed. And because there is no security parameter, this means that the efficiency of the protocol is concrete efficiency. Just the number of bits they exchange is just some numbers, it's not a function. So this also could have some implications for practical uses. Okay, so before talking about our results, I want to first show you what was already known. So first, in the multi-party setting, there are the known results, classical results by BGW and CCD, and they state that if strictly less than a third of the parties are corrupted, then we can compute any function with perfect security, and we can even do it without correlated randomness. So this can be done in the plain model. However, this assumes a lot of honest parties, strictly more than 2/3. What do we know if less than 2/3 of the parties are honest, so even in the two-party setting? So here we have the results of Ishai, Kushilevitz, Melgard, Orlandi, and Paskin-Chernyavsky, and they showed two results. The first is that if only one of the parties is supposed to receive the output, then anything can be computed with correlated randomness. However, the correlated randomness here depends on the function that they are going to compute. On the other hand, if both parties are supposed to receive this output, and the parties wish to compute the XOR of their inputs, then regardless of the correlation that they receive, this function cannot be computed with perfect security. And this even works for security with a bot, where we slightly weaken the security definition and allow the adversary to abort, and prevent the honest party from receiving its output. So even in this setting, in this weakened security definition, correlated randomness will not help the parties compute XOR with perfect security. And essentially, that's it. That's what we know. So now I want to tell you about what we did in this work. And we have two main results. Our first main result is a complete characterization of the symmetric functionalities, where the total, the number of possible outputs is at most 4. So the output is either 0, 1, 2, or 3. And interestingly, we show that our positive results also hold in the plain model, where the parties have no access to correlated randomness, while the negative results hold in the correlated randomness, and they also rule out security with a bot, just like Ishai et al.'s result I showed you on the previous slide. So what do the functionalities that can be computed look like? So I'm going to view a function, these functions as matrices. So I'm going to view, to assume that one party chooses a row, the other party chooses a column, and the output that they receive is the value that's written in the entry that they chose. So the first class of functionalities that can be computed are the trivial ones, where the function depends on only one of the inputs. The second class is what we refer to as spiral functionalities, and we gave them this name because they have this sort of spiral structures inside of the matrix. And finally, we have the class of transparent transfer functionalities. And the reason we named it this way is because this matrix can also be defined using this equation above, which is very, very similar to oblivious transfer. However, unlike oblivious transfer, the choice bit of the receiver is now revealed to the sender. And we show that these are the only families of functionalities with up to 4 outputs that can be computed with perfect security. So this is our first result. Our second result handles the case with more outputs. So this time we don't assume a bound on the total number of outputs. And we show that if the function has an embedded AND or an embedded XOR, then it cannot be computed with perfect security. And just like before, this works in the correlated hybrid model, and it rules out security with a bot as well. So what does embedded AND and embedded XOR mean? So it just means that if I look at the matrix, I can either find a 2x2 submatrix that has this XOR structure or an AND structure. So we can see it here in red. Okay, so this is our result. So now I'm going to talk about the main strategy that we have for proving these results. So I'm going to show you a general attack that is going to work regardless of the number of outputs. And before that, I will do as a warm-up, I will show you the attacker of Ishai et al. For XOR, and then I will explain why it doesn't work even for AND, where it fails, and then I will show how to fix that and how to generalize it further. And after that, the way we built all the characterization is to analyze this attack. And the way we analyze this attack is in a contrapositive way, where we assume that the attack doesn't work, and then this provides some structure on the function. So, and we try to understand what F satisfies given that the attack doesn't work. And finally, for the functionalities that remain where we know the attack doesn't work, we show I will show you a perfectly secure protocol for computing them. Okay. So how does the attack work? So I'm going to, like I said earlier, I'm going to show you first the impossibility of XOR. Right, so let's assume towards contradiction that we're given a protocol computing XOR with perfect security. And let's say that the parties execute this protocol with uniformly random bits as inputs. So the main observation here is that there exists some round, and there exists this first round, where Homer completely knows the output, regardless of all inputs and randomness. And the reason there exists this round is because the last round is an example of such round. So there must exist this first time where this happens. And similarly, we can argue the same for Marge. There exists this first round where she completely knows the output, regardless of her input, of Homer's input, and the randomness. And let's say, without loss of generality, that Homer learns the output first. So in this example, he knows this first. So this gives us the following attack. So the adversary is going to corrupt Homer. And what he will do, he will play honestly until this special round where he completely knows the output. And this is where we're going to use the fact that the protocol admits perfect security. And because it admits perfect security, I remind you there is no security parameter. So we can let this adversary compute all possible honest continuation of the protocol. So he's just going to assume, okay, what happens if I send this honest message and Marge answer with this honest message, and he's going to view this for all possible continuations. And we know that in this round, because he's supposed to learn the output, he knows that all of those honest continuation will lead to the same result. So he knows the output, so he can compute it. And what it does is that if he sees that the output is 0, he will just continue honestly. But if he sees that the output is 1, and let's say that he doesn't want the output to be 1, he will just send random messages. So intuitively, why does this work? So I remind you, before receiving this message, Marge still doesn't know the output for some values of y, and the randomness are 2. So this means that if the output is actually 1, x or y is equal to 1, there must exist some continuation that will cause her to output 0. And because Homer sends random messages, there exists a non-zero probability of Homer hitting those exact messages that will cause her to output 1. So there exists a non-zero probability of actually increasing the chance of the output of Marge being 0. So if we do the overall computation, what's the probability that Marge will output 0? Well, it's either that the original output was going to be 0, or the original output was going to be 1 times some very, very small but still non-zero epsilon of increasing it. And so we got that the output of Marge equal to 0 probability that is strictly greater than 1/2. And finally, when we compare it to the ideal world, I remind you the input of Marge is a uniform random bit. So her output in the ideal world is going to be a uniform random bit, regardless of what the simulator does. So we get that no simulator will be able to perfectly simulate the real world adversary, and therefore the protocol is insecure. So are there any questions so far?
I don't think so. Yeah.
Okay, good. Okay, so now I want to try and use this attack for end. And I claim that if we try to use the same attack as is, then the argument fails. So why is that? So let's say that we consider the same adversaries that try to bias the output of March towards 0. And if we do the same computation in the real world, we see that March output 0 with probability that is slightly more than 3/4. So where does it fail? It fails when we compare it to the ideal world. Here, I remind you that the malicious simulator can change its input. And this results in an issue because he might be able to send the input 0 with this very, very specific probability such that the output of March in the ideal world the output will increase towards 0 regardless of your input with some probability such that the probabilities are identical in both worlds. So this means that there might exist a simulator, so we can't really complete the argument. And we can do the same analysis with an adversary that tries to bias towards 1, and we can also see that it might be able to be simulatable, and so the argument failed. So how do we fix it? The way we do it is by making the following observation. And notice that if the simulator in the ideal world sent to the trusted party 0, then it doesn't receive any information from it about the input of the other party. So this suggests the idea of having the adversary to also guess the input of March, because now the simulator has a choice, either try to bias towards 0 and get no information, or send 1, get information, but he's not going to bias towards 0. And indeed, if we do the computation now, we can see that the adversary will now succeed in the attack, meaning that he will cause March to output 0, and he will be able to guess her input correctly. In the real world, this event will occur with probability that is slightly more than 1/2. But in the ideal world, like I said earlier, sending 0 will prevent him from guessing with probability more than 1/2. So he will only gain 1/2 from this strategy, and sending 1 will cause March to output 0 with probability 1/2 because their input is uniformly is a uniform random bit. And so overall, we get that the total success probability of the simulator is 1/2 in the ideal world. And so this is why AND cannot be computed with perfect security. Okay, so how do we generalize this? So we take this the same attack, and now we try to apply it to the more general case. So the parties have more inputs and possibly even more outputs. Okay, so the full way we will generalize this is the following. What we'll do is we'll take some subsets of the input. So we'll consider a subset X prime of the first party's input and the subset Y prime of the second party's input. And we're going to view the protocol as executing over only on those inputs. So honest execution will be over X prime and Y prime. And we'll also fix a subset Z prime of the output. And the goal of the adversary will be to try and bias towards Z prime. So in slightly more details, what we consider is the following. So the input of the first party is going to be a uniform random input from X prime. The input of the second party is going to be from Y prime. And the attacker does the following. Just like before, he will play honestly until reaching some special round where unlike before, he will not be able to learn the output itself, but he will be able to know if the output belongs to Z prime or not. And just like before, we know that this special round exists and everyone can compute it because there is no security parameter, so they can compute it efficiently. And if he sees that the output is indeed in Z prime, he will continue to play honestly. And otherwise, he will send random messages, hoping that it will somehow increase the probability of the other party outputting some value from Z prime. And just like we did for the AND function previously, we let the adversary try and guess the input of the other party based on the information that he has on the output. So are there any questions so far? Okay, so we have this attack. The next goal is to try and analyze when this attack works, because obviously it won't work for all functions. Like for example, the constant function, everything can be simulated. So we know that for some functions, this attack is simulatable. So the goal is to understand when. So it turns out that we need 3 conditions for the attack to work, meaning that no simulator will be able to perfectly simulate the adversary. So I'm going to exemplify this with this table below. And let's say that the set of outputs Z prime that we care about is between 0 and 3. So the first condition that we want is that interaction is necessary to know if the output is actually in Z prime or not. So this only means that in this submatrix corresponding to X prime and Y prime, there exists an output that belongs to Z prime, let's say 0 in this example, and there exists an output that doesn't belong to Z prime, let's say 4. So this only means that the parties have to interact to know this. The second criterion we have is the following. We want to say that if the adversary, intuitively, if the adversary plays honestly, so let's say that it is now a semi-honest, he will not try to send random messages like the attack before, but he will only try to hope that the output is actually in Z prime and then guess the input of the other party. What we want to have is that regardless of the input that he uses, so for any X in X prime and also for any Y in Y prime, the success probability will always be the same. So the probability that the other party will output some value from Z prime and the adversary will be able to guess the input of the other party is going to be some value P. And this P could be different for the rows and columns. And if we do the computation to try to understand what this P is, it turns out that it's directly proportional. It's directly proportional to the number of distinct entries in each row and each column. So if you want to say that that the adversary will succeed with probability P, it means that for any row, the total number of distinct outputs from Z prime is the same. So in this example, we have 2 distinct entries in every row and 3 distinct entries in every column. And intuitively, this means that if on top of this semi-honest attacker, we will also plug in the malicious attacker from before that tried to bias the output by sending random messages, he will add to this value P some small non-zero epsilon and increase its chance of succeeding. So this is the second condition that we have. But we also need a third condition that talks about what happens outside this rectangle. And the reason is that I remind you, the simulator can change its input to be some value outside of this rectangle, something from outside X prime and Y prime. So what we want to have is that intuitively playing honestly with any value X from not in X prime will not increase the success probability of the adversary. So this means that if we go to the row X prime, to the row X outside of X prime, and we count the number of distinct entries from Z prime in that row, it turns we want it to be at most 2 in this example. So we can see in this example we have the second to last row have 2 distinct outputs, so it's exactly the same as in the green area, but the last row has 0, so it's still okay. We just don't want it to be larger than that. And these 3 conditions turns out to be what, once we have these 3 conditions, it turns out that the attack works and it cannot be simulated with perfect security. So just as a very, very quick application, I want to show you why embedded AND and embedded XOR are impossible to compute. So once we have this lemma, this is a direct corollary. And I can even show you something slightly stronger than that. Okay, what I'm going to show you is the following. Let's say that we found a 2x2 submatrix that has this structure. So it has on one, let's say on the anti-diagonal, it has the same output A, and on the diagonal, it has this asterisk and B. And all I want is that A to be different from B. So you notice that if the asterisk equals to B, then we get an embedded XOR, and if it equals to A, then we get an embedded AND. But I claim that regardless of what this asterisk is, whether it's A, B, or something completely else, this function cannot be computed with perfect security. And the reason is that we can apply the lemma with the set of output Z prime equals to A. So we're going to consider adversaries that try to bias the output towards this value A. So why does this work? So the reason is that, first of all, notice that this rectangle have an output from the set Z prime that is the value A and has a value outside of Z prime, which is B. And second, notice that any row, column, regardless where you look at, will have at most one element from Z prime. So the two second conditions that we had from the previous slides will be satisfied. So we can apply the lemma, and therefore the attack will succeed. Therefore, this function cannot be computed with perfect security. Okay. So this is there a question? Okay. So this leads me to the second part of this talk, and that is to actually analyze the structure of the functions which satisfy those conditions that I stated in the lemma. You probably noticed those are not very nice conditions. It's very difficult to try and find whether there exists this submatrix with all of these very difficult conditions to check. So now I'm going to show you how we analyze this for functions of up to that have at most 4 possible outputs. So I'm going to use the fact that I just showed you that this submatrix is essentially forbidden. Once we find a 2x2 submatrix with this structure, we know that the function cannot be computed. Okay, so what about the other 2x2 submatrices that can occur? So essentially, we only have these two, which are the ABCC and ABCD, where all of these ABCD are all distinct entries. We obviously also have like constant row, constant columns, AB and AB, but those are not very interesting. So I'm going to assume that at least one of those, one of the submatrices from the below appear in my matrix. Okay, and what I want you to first notice is that the second matrix, this ABCD, is what we call sort of potentially forbidden, because we might consider adversaries to try to bias towards A and D, for example, the diagonal. But unlike the forbidden matrix, it may be possible that the overall function can be computed because of what happens outside of the matrix, outside of this sub-matrix. So the idea is in the characterization is to look for these submatrices, apply the lemma, and get and learn about the structure of what happens outside of these submatrices. Okay, so first I'm going to assume that first of all there is no forbidden submatrix. This is because I want to assume that the function can be computed, and so the attack doesn't work, and this will induce some structure on the function, which I'm trying to understand. But for now, I want to assume that there is also no ABCD, so this potentially forbidden submatrix doesn't appear as well. So I claim now that the function is spiral. For example, it could be of this form on the right. And the main lemma towards proving this is that there must exist either a constant row or a constant column, but not both. So why is this true? So first of all, I'm going to show you that if we prove this lemma, then the theorem is directly implied from it. So let's say that we found, for example, 2 constant rows. Let's say that both of them has only 3 in them. And let's look at the other entries in the matrix. So first of all, can this asterisk be equal to 3, for example? Well, notice that if that asterisk equals to 3, then we are already very, very close to having a forbidden submatrix because of the diagonals of 3s. So this means that those other asterisks in the same row must also be equal to 3. So we can actually take that rows of 3 and add it to the rows of 3 from below at the bottom. So we can assume without loss of generalities that all of those stars are not equal to 3 and that those rows of 3 at the bottoms are everything that we have. And once we have that, we can remove them and now ask what happens on the matrix that we're ended up with. And it turns out that, again, we can apply this lemma. It will have a constant row or a constant column, but not both, so we can continue inductively on this matrix, and each time we'll remove some rows or some columns until we reach a constant matrix. Okay, so all that is left is to actually prove the lemma, that there is either a constant row or a constant column. So the proof is done by contradiction, so let's assume that there is no constant row and no constant column. So first we're going to pick some row. So we know that it's not constant. So let's say that we found 0 and 1 on this row. And we know that the column that contains 0 is also not constant. So let's say that it contains a 2 somewhere. We know that it cannot contain a 1, because if it contains a 1, then it will be a forbidden submatrix. Then it must contain some other value 2. So now we can split into two cases. What happens in that asterisk that completes to this rectangle? So it can either be 2 or 1. Because notice that if it equals to some other value 3, then it's an ABCD, which we assume that we don't have. So it must be 2 or 1. So without loss of generality, we can assume that we're in the first case. And now we'll try to fill in the gaps, these asterisks. What do they equal to? So first, I claim that if I go to this position, right next to the 2, then it must be 3. Why is that? Well, because the row is not constant. So it must contain something that is not 2. But notice it cannot be equal to 0 or 1, because then we'll have a forbidden submatrix. So it must be some value 3. So what happens above and below this 3? So notice that, again, if, for example, I take the top row to have a 0 in it, then we have 1, 0, 2, 3, which is exactly the same as an ABCD, which we assume to not exist. So it cannot be a 0. Similarly, it cannot be a 1. And finally, it cannot be a 2, because now we have a forbidden submatrix. And because we assume we only have at most 4 outputs, it means that it must be equal to 3. And we can do the same argument for any other value in the column and get that this entire column must be constant. So we got a contradiction, and therefore there must exist either a constant row or a constant column, but not both. Okay, so this was the first case where we assume that there is no this ABCD structure inside. So let's assume that now there is an ABCD somewhere inside the matrix. So let's assume that we found a 0, 1, 2, 3. So now I'm going to apply the lemma for the sets Z prime, 0, and 3. So basically, I'm going to consider adversaries that try to bias towards the set 0 and 3, and I'm going to assume that the parties both play with the two inputs that corresponds to these rows and columns for this submatrix. So if I apply the lemma, I remind you that we can get one of two things from it, because the lemma states that if the adversary cannot bias towards 2 and 3, it can bias towards 2 and 3, but can still be simulated, then something must happen outside of this rectangle. And it turns out that either there exists a row where it has this 0 and 3, or it has a column corresponding to those same rows that has a 0 and 3 in them. So the lemma implies because we assume that the function can be computed, the lemma implies that one of these must happen. Okay, so without loss of generality, let's assume that the former holds. Okay, so we dealt with one diagonal. What happens with the second diagonal? So we can apply the same lemma for that diagonal. So we consider adversaries that try to bias towards 1 and 2. And again, we get two situations. Either the row contains 2 and 1, or the column, or a column next to it containing 1 and 2. So one of these two must occur. But notice that the left one is impossible, because there is no way to fill in this asterisk without generating a forbidden submatrix. So for example, if it's equal to 3, then it's very simple to see that we have an embedded end. And it turns out that no other value can also be there, because then we'll have an embedded end, and we know that it implies the function cannot be computed. Okay, so we get that this structure is impossible, so we are left with the one on the left. But notice now that this entire 4x2 submatrix corresponding to these 8 entries is exactly the transparent transfer structure that I defined earlier. And just using a little bit more work, very, very similar to what I did so far, we can show that any other column or row is just a copy of this transparent transfer structure. Okay, so essentially we start with a transparent transfer submatrix, and every other row and column is just duplication of the columns and rows, the transparent transfer. So they don't add any real value for the parties. And that's it. That's how we got the negative results for our characterization. Okay, so now I want to talk about the positive results. This is so I'm going to show this only as an example for the transparent transfer. All of the examples, I remind you, all of our positive results, I remind you, they're going to work in the plane model without any correlated randomness, and in fact, there are going to be no randomness at all. The protocols are going to be completely deterministic. Okay, so how does the protocol looks like? So let's say that Homer holds some row as an input and Marge holds some column as an input. So the protocol is very, very simple. Marge will send her input to Homer, and then Homer will compute the output and send it back to Marge. And I claim that this protocol admits perfect security. So first of all, notice that corrupt Marge can't do anything because she only sends her input. So all she can do is change her input, but that's what we allow in the ideal world. So simulating her is very, very simple. So let's consider a malicious Homer. So what can he do? The only thing that he can do is change the output that he sends to Marge to something that depends on the input that he receives from Marge. So for example, he could send 0 if he receives a 1 from Marge, and sends 3 if he receives 2 from Marge. But notice that this is exactly the same row that corresponds to a 0, 3. So this is exactly the third row in the matrix. So even though he can choose the output of Marge, based on her input, the simulator can do the same. This will just correspond to changing its input to something else. So the simulator can send this input to the trusted party, force Marge to output the same thing as in the same output as in the real world, and also learn her input, because whether he receives 0 or 3 completely reveals to him the input of Marge. So this is the reason the protocol is secure, and a very, very similar protocol works also for spiral functionalities. So just to summarize, we consider perfect security for 2 parties with correlated randomness. We completely characterize functionalities with up to 4 possible outputs. This follows from a more general negative result, which also show that embedded end and embedded XOR are impossible to compute with perfect security, regardless of the number of outputs. I didn't talk about it, but it turns out that our impossibility result also worked for security with a board, just like Isha et al. Result worked for this setting. And finally, we even showed that there are some interesting families of functionalities that can be computed with perfect security in the plain model. So just as future work, so it's very natural to ask what happens if the function has more than 4 outputs. In particular, a very interesting question to ask is, if the function cannot be computed with perfect security, does that mean that our attack works? So is our attack sort of complete in a sense? Does it capture, can we completely characterize everything using just this one attack? In a follow-up work we did, it seems that it's true for 5 outputs, it seems even for more than 5 outputs, but we're still not really sure about it, but it seems like this is the case. Another question is relation to the semi-honest setting. So here I remind you that a work by Kushilevitz, he showed that a function can be computed with semi-honest security if it is decomposable. So decomposable just means that you can take the matrix, split it into 2 either by separating it according to rows or columns, such that there are no common entries. Roughly, this is what it means. There are no common entries after we split the matrix into 2. So is there a relation from that to what we did? Because it seems like this decomposability also appears in the spiral and the transparent transfer functionality. So is it true that there is some relation? Another interesting direction is to also consider asymmetric functions. So what we consider in this work is the case where both parties receive the same output. But we also have a complement result from Isha et al. That say that if only one party receives the output, then everything can be computed with perfect security, assuming the parties have the correct correlation. And finally, what happens in the multi-party setting, with or without broadcast? So we know that from BGW and CCD that if there are sufficiently many honest parties, then everything can be computed. What happens if there are at least a third corrupted parties? So can we say anything interesting about that setting? And that's it. Thank you.